So I would like also to thank all the organizers of the meeting to invite me. So in my speech, I will talk about the analysis of spatial multivariate structure. So as you know, in many fields, we can collect data under the form of tables for which you have the measurement of a number of variables for a series of individuals. And in this case, techniques of multivariate analysis, such as PCA, CA, and so on, provide efficient tools to summarize the structure of these data sets. But in many instances, these individuals can correspond to entities for which we have spatial information. So, for instance, it can correspond to geographical, to administrative units that can be plotted on a map, or to, in the case of ecology, or to location in a study area for which we can collect the spatial properties, for instance, using GPS technology. So in this case, one may be interested not only to study the covariation between the variables, so the multivariate structure, but also in the spatial patterns of this multivariate structure. So for instance, in community ecology, as showed Kayo, we are very interested in tables in which we measure the abundance of species, so animals or plants, in a number of sites. And community ecology will try to understand the organization and the functioning of assemblages of species that coexist. And as shown Kayo, environmental variability is usually an important driver of the organization of biodiversity. And so you can introduce this information using a second table and use a two-table ordination method such as CCA to study the structure of the community that can be explained by the environment. But usually these sites are sampled in space, and we can have a geographic coordinate for this site. And in this case, the information in this table can be represented as a series of maps. So here, each map corresponds to the distribution of a species. So here we have data on vegetation. And we can show that the distribution of species is rarely random. It's usually very strongly structured in space. So we can be interested to study this, the common spatial structure of the different distribution that we observe. So when we are studying community ecology, we can identify two main sources of spatial structure. The first one is to consider that we have an environmental gradient. So here, for instance, elevation, and we assume that the species, the distribution of species is related to this gradient. So it's what Kayo says, that we have unimodal response curve, for instance. And in this case, the distribution of the species will be related to the environment. And as the environment is spatially structured, we will obtain a spatial structure in the distribution of the species. So here we have a spatial structure which is induced by the explanatory variable, which is the environment. Here we have a second example where so we have also a distribution of the species which is strongly structured in space. So this is not real data. it's a simulated data. But here, the distribution of the spaces the structure that we observe is completely orthogonal to the environment. And in this case, we can have another type of process that is responsible of this type of organization is the fact that we are studying different species and we can have biotic interaction between species. So for instance, here we have a black species, and we can say that the white one is a predator or a competitor of this species. And so the spatial distribution of the species will be shaped by the distribution of the other one. So in community ecology, we are now really interested to try to disentangle these two types of ecological processes, so environmental related processes or biotic interaction processes. And as spatial patterns may originate from these two types of processes, we need tools to be able to disentangle these two types of structure to infer the ecological processes that are responsible of this type of structure. So we need tools that will integrate the multivariate aspect, because we are interested in multiple species data sets, and also the spatial aspect, because we are studying the spatial structuring of the distribution of species. So so here it's a problem of community ecology, but I think that it's a much more general problem, question at least. And Michael Friendly, in a very nice paper in 2007, analyzed and revived André-Michel Geary and show that when you have to deal with spatial and multivariate analysis, we can have 2 points of view on this type of data sets. So the first point of view is to use a data-centric display. And in this case, what you will do is to work on the multivariate structure, to try to summarize the multivariate structure, for instance, using CA, PCA, and so on, so eigendecomposition-based method. And then you can try to introduce the spatial information on the output of the multivariate analysis. So in the first approach, you will treat the multivariate problem first, and then you introduce the geographical information to interpret the result. On the other hand, you have he defined a map-centric approach. So it's mainly based on multivariate mapping techniques. So in these techniques, what you do is to use multivariate symbols such as Chernoff faces and so on a map. So here you will use a map as a way to present the result, and you use multivariate symbols to display the multivariate aspect of the data set. But of course, in this case, you mostly focus on the geographical information, and you didn't summarize the covariation between the variables, as multivariate analysis does. So in his paper, he says that, of course, the integration of this data-centric and map-centric visualization and tools analysis is still incomplete. And he says that there is a real challenge to develop new methods that will integrate both multivariate and spatial aspects into a single framework. And this is what we can call a family of methods that will treat both aspects simultaneously, is the framework of spatial multivariate analysis. So in community ecology, there have been, since I think the last 2 or 3 decades, a development of several techniques that try to introduce both multivariate and spatial aspect into a single analysis, so that we can optimize both parts simultaneously. So in my presentation, I will first present some methods to analyze either the multivariate or the spatial aspect separately, and show after how we can develop new methods that integrates both aspects in the same analysis. So to illustrate my talk, I will not use a community ecology example, but I will use the example of Michael. So this is the data set that has been collected by André Michel Geary. So this data set, as you can see, is quite old. It's one of the first social data analysis. So Geary collects a number of variables. In my example, I will take 6 variables that describe the morale in France in 80-30. So in my talk, I will use the 85 department of France. So here you have an original map of Geary, and 6 variables that describe the criminality, the level of literacy, the donation to the poor, the number of illegitimate births, and the level of suicides. And for all these variables, as we have some transformation for all these variables, large number will correspond to morally better department. So it's quite interesting to see that in more than a lot of time ago, that Geary he used only maps and graphics, and still try to consider both multivariate and geographical aspects. So when you try to analyze a multivariate dataset, so it's a very quick view. When you try to analyze a multivariate dataset, you can use a multivariate analysis, and we can define this analysis as a triplet of X, which contains the data or transformed data table, Q, which can be seen as a metric for the individuals, and D, which can be seen as a matrix for the variables. And a multivariate analysis can be seen as can be summarized as a triplet, which lead to 2 eigen decomposition, which are closely related, and we can, with this diagonalization, we obtain the principal component and the principal axis. So in both spaces, and this analysis maximize these quadratic forms, which are equal to eigenvalues. So when we apply a multivariate analysis on Geary's data, we can, so here, as we have different type of variables, I used a PCA and correlation matrix, which correspond to this triplet. So here we just have the scaled variables, here the identity matrix, and here the diagonal matrix with 1 divided by n on the diagonal. And here you have the biplots, which represents the variables and the department as points. So here you can see the bar plot of eigenvalues. So it suggests that there is one very important dimension, and we have 2 other here. So it would rather suggest one-dimensional or 3-dimensional interpretation, but for the clarity of the display, I will use a 2-dimensional representation, even if I know that it's perhaps not the best one. So here you see that the first axis of this PCA separate departments here that has a high level of literacy, And here, that has a low level because due to the transformation of the variables, so they have a low level of crime against property, suicide, and illegitimate birth. So here we take into account only the multivariate aspect, and what I said that if you want to introduce the geographical information, one thing that you can do is to try to project on this biplot the geographical information as additional information. So for instance, in this data set, we have a partitioning of France into 5 regions. So I don't know if it's really administrative region or not. But here we have 5 regions, so north, west, east, south, and center. And we can represent these different regions using colors, and then represent each department by a symbol for which the color is related to its region. So here, for instance, it helps to interpret the result in a geographical context, because here you see that we have most of the purple and green points that are in this side. So it means that department that has a high level of literacy are mainly in the north and in the eastern part of France. So here, with these simple tools, you can have an interpretation of the geographic properties of the multivariate structure. But of course, this is not optimal in the spatial point of view, because we analyze the multivariate structure in the first step, and then we only add geographical information a posteriori. So there is no optimization of the spatial aspect. So in the world of geography, there is many tools that have been developed to measure and test the strength of the spatial structure. But most of these tools are univariate techniques, and the mainly used indices to evaluate and measure spatial structure are spatial autocorrelation statistics, such as Moran index and Geary's ratio. So the autocorrelation tools are based on the principle that we have to firstly define a template that represents the possible spatial interaction between the individuals. So this possible spatial interaction can be represented as an n by n matrix, which is a mathematical representation of the geographical layout of the region under study. So in the easier way, this spatial weighting matrix can be obtained using a connectivity matrix, where we will say that 2 departments are neighbors, and in this case, I will put a 1 in this matrix, and we will say that 2 departments are not neighbors, and in this case, we will put a 0 on this matrix. So this information can be represented on the geographical map under the form of a graph, and in this graph, so nodes correspond to department, edges correspond to the links. So here I say that these 2 departments are neighbors. So I have a link, and this corresponds to a 1 in the connectivity matrix. So here you have a very simple way to, in the case of aerial data, we can say that, for instance, 2 departments are neighbors if they have a common boundary. But you can use more complex design to define this matrix. For instance, you can take into account the length of the common boundary. And in geography, usually they didn't use this matrix. They used a standardized version of this matrix. And in geography, the The mostly used standardization is a row sum standardization. So all you have to do is to take your connectivity matrix, for instance, and you divide the value by the sum of the rows. So I will go back later on the interest of this standardization. So when you have defined your spatial weighting matrix, now you can compute autocorrelation to measure the intensity of the spatial structure. So as I said, two main indices exist. So firstly, you have the Moran coefficient, and here the Geary's ratio. So here you have the usual definition of these indices. So they aim to measure exactly the same things. They aim to measure the intensity of the spatial structure, but they are based on very different principles to do that. Geary's ratio, so it considers, here you have the W matrix, so it considers neighbors, and what you will do is to evaluate the autocorrelation by measuring the difference, so here the square difference between neighboring observations. So here you will see autocorrelation by measuring the difference between the neighboring observation. And as you can see that here we have squared values, so this index will always be positive. On the other hand, you have Moran coefficient, and Moran coefficient will measure the spatial autocorrelation using also the W matrix. So you will measure the similarity between neighboring values, and here you will measure so here you measure the difference, but here you will measure the similarity, a kind of similarity, by computing the product of the centered values. So if I consider the Moran coefficient, you can so with the formula you can measure the autocorrelation, and then you can test it. So there are different ways to test it. One easy way is to permute the observed value among the department, for instance, and to obtain a random distribution of the Moran coefficient under the hypothesis that data are randomly distributed. Then you can test your observed value compared to this distribution of a random value. So here, if Moran is higher than what you can obtain under random assumption, then you will have a positive autocorrelation, meaning that neighboring values are more similar than one I can expect under random distribution. On the other hand, if you obtain a value of Moran coefficient that is lower than what you obtain under random distribution, then you can say that I have negative autocorrelation, meaning that neighboring values are more dissimilar than what I can expect under random distribution. So if I apply Moran coefficient to the data of Geary, you can see that I have only positive autocorrelation, because here I have only positive values. Sorry. And here you have the p-values obtained by Monte Carlo simulation, and you can see that all the variables are highly significantly autocorrelated and positively autocorrelated. But of course, here what I did is I use spatial autocorrelation tools, but I consider the multivariate aspect by doing multiple univariate analysis. And of course, here I don't consider the redundancy between the variables. So I come back to the row standardization of the spatial weighting matrix, because it has a very, very nice interpretation that has been given by Ancelin. So if you consider the row standardized spatial weighting matrix, then you can define a lag vector. So in this vector, it has exactly the same length as the vector of observed value, but in this vector, each observation is replaced by the average of its neighbors. And in this case, you can rewrite Moran coefficient as a ratio of two inner products. So here you have the variance. And here, the numerator, it appears that Moran coefficient measures the spatial autocorrelation by doing the inner product of the observation by the lag vector. So by a vector that contains the average of the neighboring values. And Ancelin proposed then to represent these two vectors in a B-plot, where each point corresponds to a department. And here in abscisse, you have the value of the original variables, and in ordinate, you have its lagged version. So here, for one point, here I have the observed value, and here you have the average of its neighbors. And Ancelin shows that here you can apply a linear regression on this scatter plot, and the slope of this linear regression gives exactly the value of Moran coefficient. So this is a nice tool because it allows to visualize in a scatter plot the autocorrelation, which is usually summarized by one number, and it allows to detect outliers. So here, for instance, you have the department of the Hautes-Alpes, which is characterized by a high level of literacy, but you can see that its neighbors have quite a low level of literacy compared to what you have in the Hautes-Alpes. So one first step to go to consider both multivariate and spatial autocorrelation is to apply these tools of spatial autocorrelation on the output of multivariate analysis. So in the first example that I showed at the beginning, I show you how you can introduce the geographical information in the multivariate space, and now what you can do is to use the multivariate information and to introduce it in the geographical world. So here, what you can do, for instance, is to map the PCA score and to compute autocorrelation measure on this score. So here I add a reference to Goodall in 1954. So I think this is the first use of PCA in ecology. And in this paper, Goodall represents the PCA score using contour lines. So to produce map of the main structure of vegetation, and he tried to compare this map with maps of the environmental variability. So here you can see that we separate, for instance, the first axis separates clearly the fronts in two parts. So here you have the low value on the first PCA score, and here the high value on the first PCA score, and on the first PCA axis, sorry. And here, this corresponds to high level of literacy, and it's this partitioning corresponds closely to the partitioning of France between the France éclairée here and here the France obscure. So this type of approach are very simple to handle because they only use quite simple tools, but it's the same stuff. Here you consider the spatial aspect only in the second step. So if you want to consider both aspects simultaneously, you have to consider the multivariate and the geographical aspect. And several techniques have been developed in community ecology. So usually these methods consider the multivariate aspect using classical techniques of dimensionality reduction. And different alternatives can be used to integrate the spatial information. So for instance, you can consider space as a partitioning. So it's what I show with the region, with the partitioning between the five regions. You can try to introduce space using spatial explanatory variables, but you can also try to introduce space using a graph and a spatial weighting matrix directly in the analysis. So it's why I will try to present now. So the first case is to consider space as a partition. So here I have my original table. I have a partitioning of space on a map. And of course, this spatial partitioning corresponds to a partitioning of the row of my original table. So in this case, if you want to study the spatial patterns, what you do is to try to maximize the difference between the region. You want to see how a region differs. And in this case, there are many methods, because here you just have to consider one table and one partition of the row. So there are many methods, such as discriminant analysis, to do this stuff. Here I used between group analysis, which is simply, so here I consider my original data analysis. Here I have a dummy table that represents the partitioning of the rows between the different regions. And here you define a new triplet, where here you have a matrix where you have the region in row and the variables in column, and the value are the average value of variables for the region. And you define a diagonal matrix of weight, which is simply based on the number of departments per region. So when you apply this analysis to Geary's dataset, so you can see that you explain 30% of the total inertia, of the total variance. So there is 30% of the total variance which is explained by this partitioning. And here we show that as in that the analysis, so it maximizes the separation between the region. So here you have the map that integrates this information. So you can see that the variable the result for the variables is closely linked to what we obtain with PCA, but here you optimize the separation between the region, and you see that here on the eastern part, so you find the north and the eastern region, and all the other region on the right part of the axis. And the second axis mostly separates the south from the south and a little bit the east from the west and the north of the country. So okay, this is a nice approach, but it has the main disadvantage to require a partitioning of space into, for instance, region. So it can be useful when you have such partitioning, but of course, it is not always the case. So what we can do is to try to integrate space using explanatory variables. So here I just use the formulation of Tukey that says that usually in data what you can see is a trend and a random variation. So if you are interested, for instance, by time series, so it's what did a student in 1914, you can say that I can represent data as a function of time. So here, for instance, he used a polynomial of time. So this corresponds to the trend, and then I have a random variation or variations that are not related to time. So students say that, of course, he used this approach for time series, but we can also use polynomial in the case of spatial data. So when I consider my Geary's dataset, I can define a polynomials of geographical coordinates. For instance, here you have the x that's allowed to separate the eastern part from the western part. You have the y that's allowed to partition France between the north and the south, and you can have the square and the product. And you can say that with this geographical polynomials, you can define different type of spatial structure. But in the case of student, we were in the univariate case, and here we have to deal with multivariate response. So here, what I have is a triplet, so the analysis of one table and a table of spatial explanatory variables. So in this case, what I can do is a principal component analysis on instrumental variables, So here, the analysis, it just, so you take the initial triplet and you just replace the original table by a table of predicted values. So what I do is a multivariate regression, or I explain X by the explanatory variables in Z. So of course, this is exactly redundancy analysis when I consider PCA on X. It is canonical correspondence analysis. Wow. Okay. So this is canonical correspondence analysis when you consider CA on X, and between class analysis when you consider here categorical variables. So after you can do a principal component analysis using these spatial explanatory variables, and here the analysis of a spatial structure relates to the analysis of the variance that is explained by space. So I apply this to Geary's data set, and it returns quite the same result of PCA and other analysis. So here I have another approach, but I have no time. But it's another way to define spatial explanatory variables, which is much more clean, I think. But I will go to the last part, which is, I think, the most interesting. It is how we can introduce spatial structure directly under the form of the spatial weighting matrix. So this approach has been initially developed on the Geary's ratio by Ludovic Lebar, and he shows that we can rewrite Geary's ratio using a matrix formula here, and he proposed to diagonalize a matrix of local covariance. So this approach was, I think, the first attempt to introduce directly the spatial weighting or connectivity matrix in a multivariate analysis. So it has the main advantage that here we have a positive definite matrix. It has been extended to CA, but I think that one problem with this approach is that it maximizes, it's based on Geary's ratio, so it maximizes the local difference between the observation, while we are mainly interested in the smooth structure. So not in the local difference, but more in the local resemblance. So Wartenberg in 1985 proposed a first approach based on Moran coefficient, and he proposed to diagonalize this matrix. And in this paper, he says that main difference between his approach and PCA is that this approach, this matrix is not positive definite, and so you can have a multivariate analysis that produce negative eigenvalues. And these negative eigenvalues are not too much discussed in the paper, but they correspond to spatial structure with a negative autocorrelation. So the problem here, it only considers symmetric and binary connectivity matrix, and it considers only the case of normed PCA. So here are other stuff, but I will just go to the last method. It's generalization of this approach to the row standardized spatial weighting matrix, because this has very interesting properties in terms of interpretation, and this extension to the case of any one-table ordination methods, including, for instance, correspondence analysis. So here we have defined an analysis that is related to, that corresponds to this triplet. And the principle behind the method is to define a lag matrix in the same way that we define a lag vector. So lag matrix will be a matrix with each lag vector in column. And we can show that if we define an analysis that corresponds to a coinertia analysis between the lag matrix and the original matrix, we obtain a linear combination of the variables that maximize this quantity. And we can show that this quantity is simply equal to the product of the criteria usually maximized in the multivariate analysis. So for instance, the variance in the case of PCA by spatial autocorrelation. So in this approach, instead of maximizing only the variance, only the structure, you will maximize the product of the structure and spatial autocorrelation. So you will find spatial structure. So this analysis is based on this diagonalization, and I don't talk about that, but it has interesting properties. So here are the output of the analysis. So in this case, the eigenvalues, in this case, the eigenvalues are equal to the product, as I say, of the variance by the Moran coefficient, by the autocorrelation. So here, what you maximize, the eigenvalue, is the product of the variance. So this is a criteria of the original analysis by the Moran coefficient. And as I said, the Moran coefficient can be seen as a relationship, as a correlation between the observed score and the lagged score. The lagged, okay? Not so clear, but it's a little bit fast. And so in this case, you have a B plot, where here you have the score of the department, and you have at the other, so the beginning of an arrow is the score of a department, and here you have here at the other part of the arrow you have the mean, the average of its neighbors. So you have a kind of local indicator of spatial association, meaning that a long arrow will mean that one department is very different from its neighbors. So to conclude, I just say that so there is a lot of here we have a very simple structure, which is one data set with spatial information. That there is many methods that exist to try to introduce these two aspects simultaneously. If you want to have a deeper view, there is a paper to be published in Annals of Applied Statistics in a special issue on multivariate analysis. With Michael, we have a Geary package on Cran that contains a vignette, and this vignette allows to reproduce all the analysis that I have presented here, and that are also described in the paper. Just to say that in many cases, the results returned by spatial multivariate analysis are very similar to those that you can obtain with simple analysis. So we can just ask why we have to include space in this analysis. So here you have an example where I used CA, and CA was really bad because it was very greatly influenced by rare spaces. And here, when you introduce the spatial constraint, it allows to discover structures that are not visible with classical analysis. And just I finish now. Just to say that there are, here I talk about spatial structure, but this type of approach can be generalized to any constraint that can be introduced under the form of a similarity matrix. So if you have here I have my W matrix, which represents the links between the spatial neighbors, but you can have any type of similarities that can be coded under this form, and so you can introduce many type of constraint in multivariate analysis. And some project is to include constraint on both row and columns, or to consider a series of tables with one type of constraint. Okay, sorry, and thanks.